next group is my group, and I worked on this project with Harry. And our project is basic. Oh, Harry, you can wave hi if you want. Okay, so our project is about creating an artificial ballet teacher that gives corrections to student dancers using artificial intelligence. So how we came up with this idea is that um, kind of during the beginning of the pandemic, when many physical education classes, such as ballet, were forced to shut down, again, due to COVID. And we thought it would be a good idea if we can find ways of turning, professional videos, such as, videos of professional dancers dancing, which are open source videos, and turning that into useful and accessible feedback. And we thought that doing this would be worthwhile since private coaching is also very expensive, and getting the proper feedback to achieve proper technique, in this case in ballet, which is such as body alignment, is crucial for injury prevention. And yeah, so the first thing we did was kind of do some background research, right? We found we researched previous programs that are similar, that do similar things, and we found one common flaw, and that flaw was that um, the programs only really focused on pose recognition by using convolutional neural networks to classify the poses. And really all they did was look at, dancers' poses at certain moments of the pirouette. So for example, they're facing the front or facing the side, and they never really take into account into the actual movement, um, like over a time series. So with that, they're unable to provide actual useful feedback to the dancer or to the user, and which is why hold on, next slide, which is why to better these kind of feedback programs, we propose a program that does kind of three things. So the first is, with the input of the student dancer's single view video, it will be able to identify students' mistake and compute a percent depicting the accuracy, and then finally outputting a user-friendly feedback. And here's our hypothesis. So we propose a new method, um, and our hypothesis would be that if a new feedback system uses a feature angle extraction system as a medium for the accuracy evaluation and employs data from neighboring frames, its evaluation of dancers' movements will increase in accuracy and helpfulness. Since more information regarding the dancer's movement are optimized when outputting the final feedback, and we'll talk about that more. So. And also, just to go back to the slide, this is just a video of the pirouette, and this is the type of turn that we decided to focus on for our program. But just so you guys know, this general pipeline that we propose, it can be very easily applied to other movements as well, such as other sports or other dance poses or movements. Cool. So I'll pass it on to Harry.
Yeah, so this is a general pipeline overview of our application, including creating the teacher model using professional videos that can be found on YouTube or other open source websites. That's shown with the purple arrows, and then the processing of the student video by breaking it up into individual frames, getting the pose, and then analyzing it, finding mistakes, stuff like that. That's all shown in the blue arrows, and that finally results in the user-friendly feedback all the way at the bottom right.
Okay, so now talking about the data set and the ground truth. So you may ask, where do we actually find the videos, and how do we actually create a teacher model? So we collect from YouTube. We collect 20 teacher videos, which together is a lot of joints of professional ballerinas performing 2 rotations of the pirouette, and we use those videos to basically train our teacher model, and we'll talk about that later. And we made sure that our video data are from top tier ballet companies from worldwide, and we also accounted for different, various ballet body types, such as height, different body types in general. And we also made sure that our data set are approved by like 9 award-winning actual human ballet teachers, and we surveyed them. And in terms of the student videos, there are 25 videos involved that we found. They're open source, so basically free to use. And we also conducted this survey again from the 9 ballet teachers that we surveyed, and we ask them to provide feedback for all of the student videos. So then later on, we can see how our program is doing. So we use that as a basis or as a ground truth for the types of feedback that we give. Okay.
The software that we use to identify the poses in each of our video frames is OpenPose. We chose this program because it gives 3D coordinates, so X, Y, and Z data for each key point that it identifies, and it can find multiple people in a single frame if necessary, so it's not limited to one person. And it's also really efficient and accurate, so that's why we went with this program.
Yeah.
We face two main challenges making this program. The first being that OpenPose sometimes gives noisy key points, which are basically inaccurate because it misidentifies a key joint in a frame. And we compensated for this using the median filter, which diminishes unwanted noise by essentially replacing those outlying points with more of the average kind of data. And then the second main problem is variance in teacher and student videos, because not every ballet performer is going to have the same body type, like we said earlier, and they're not going to perform the pose at the same speed, but that doesn't necessarily make them wrong. So the first way we fix that is using an angle parser, which Emily will expand on more in a second. But basically, we realized that the only defining factor of a pose are the angles of the joints. So we can disregard all of the other factors that other programs try to analyze, like limb lengths and stuff like that. And then the second thing that we use to accommodate for these differences is dynamic time warping, which aligns the two videos, which aligns the frames of the two videos, sorry. So even if they're going at different speeds, we can sort of slow it down or speed it up accordingly so that we can accurately compare the student and teacher videos.
Right. Okay, so now we can talk about the angle parser, in which we coded with Python. And so basically what it is that for all of our videos, we first pass it through OpenPose, the human pose estimator, right? So then what outputs from that is the XYZ key points. And then using those, like Harry said, we have to convert them into a format in which we want them to serve as good indicators for correct and incorrect movements. So what we did is we basically use trigonometry to convert the XYZ coordinates of all of the videos for all of the joint angles, all of the joint segments, and we turn those into angles. And as you can see on top, we actually created two types of angles, so then it captures the 3D aspects. So one is from the side view and one is from the front view. And as you can see on the bottom left, those are just sample outputs of the XYZ key points from OpenPose that are computed, and then we store them as JSON files for all of them, for all of the joints. And then later on, the same types of angles for the same type of joints are going to be compared, and that's basically how we get the feedback between the student and the teacher, if that makes sense. Yep. So next we have dynamic time warping.
Right, so this is the all of the student and teacher frames in order to compare them. Basically what this does is it takes, for each angle, this goes one angle at a time, so we have to do this for every angle, one after another. What it does is it takes the difference between the angles for every frame and sees where there is the smallest difference. And then that's like the ideal match for the two frames that we should be comparing. So when we do this for every single angle, we can combine that into a bunch of index pairs, which will tell us basically this frame corresponds to this other frame, and these two are the ones that you should compare in order to give the most accurate feedback. And then because we do this one angle at a time, we end up with, I think, 28 total index pair lists. And then we need to combine that into one so that we can compare each video frame. We do that using a combination of mean, median, and mode, and the technique that we use is dependent on the distribution of the data. So if, say, it's distributed like the graph on the left, it's a normal distribution, then we're going to use mean to, bring all of these matches down into a single one. But if it's distributed more like the right, for example, then we're going to use the median because that is um, the technique that best accounts for the outlying values on the right tail of the graph.
Yep. And so after dynamic time warping, in which we get the correct frame matches, so the next step we need to do is to actually figure out like what joint angles are important to study, because like a real human ballet teacher, this program actually needs to know what to look for, right, in the good pirouette versus in the bad one. So how we conquer this problem is that we use an angle-based feature extraction process, um, which identifies the important angle features of a correct pirouette. And we do this with two approaches. One is using a random forest classification, and the second is a verification approach, in which it's basically the important angle features identified by the like real human ballet teachers to verify approach number one. So our approach number one, basically what it is um, it for all of the teacher videos that we have for our training data set, it studies the correlation between important feature and between the angle feature, um, so then it finds the most important features and the angle features that actually have the strongest correlation. And the results that we get from this, which are highlighted on the right, on the red box, inside the red box, and so these are the four features that are the most important, or our model found the strongest correlation for. And it is also verified by the 9 award-winning ballet teachers that we surveyed from earlier. And the next step we have is to create the actual teacher model. So what we do is that we combine all of the training data for all of the teacher videos. We run it through all of our previous processes, and then we finally compute a teacher model that is essentially a threshold of accepted values for each type of feature. And we do this using this complicated math model that we developed, although it really is just the mean of the teacher angles plus minus the standard deviation of the teacher data set. And we do this for every single feature. So then for every single feature, we have a threshold for the correct values. And then how we evaluate if the student videos are correct or not is we run it through our previous processes, like I said before. And then so the percent correctness that we output, which is the percent accuracy depiction, would be the number of frames within the allowed thresholds divided by the total amount of matches that we have. So that's how we find the accuracy percentage. But then, simply evaluating the accuracy percentage for the student dancer is not, the most useful feedback. This is why we use decision tree classifiers to store pre-written feedbacks and they're returned to a dancer with this DTC. And so the DTC, there are basically four, one for each feature that we identify from earlier, and the decision tree classifiers are trained to give the final feedback to the dancer by asking itself questions based upon previously computed information, such as the joint angles or at which the frames for the student is labeled as incorrect. And that's how we um, basically give the final feedback. And the feedback would be, in terms of readable words. And yeah. So then we can start to test our data, and I'll pass that on to Harry.
Right, so the graph on the right here is some of the results of comparing the student video with the teacher model. The student video is in blue and the teacher model is in red. As we can see, there is a general trend that both of the videos follow, although sometimes the humps and dips come in different places, which is why DTW is necessary to align these two sequences. And then even when we do align them, we can see that there are some outlying points, right? So at the beginning, there's that one blue point, and then in the middle, there are some other blue points. that stick out, and those are the kinds of discrepancies that we're trying to provide feedback for. And then the videos that correlate with these are shown, or at least the frames from the videos are shown on the left here, so we can see how these little mistakes are being represented on the graph, and then how we can turn these differences into applicable data for our users.
Right. So now we have the quantitative results, and so when we test our data, we basically wanted to see a few things. The first thing is that we want to see is our method of using the angles actually a good choice, or like basically does it actually do a good job, and remember at doing its job, which remember that its job is to filter out the variances in different videos that might affect the feedback, and so if you look at the results for the teacher videos tested, there are actually 20 in total videos, but these are just the 4 videos selected at random for the teacher and the student. And the teacher videos from the testing data set, as you can see, outputs an overall correctness ratings ranging from 0.98 to 1.0, in which it just means 98 to 100%. And since having an overall rating close to 1.0 signifies that at every frame of the video, all of the feature angles are within the allowed thresholds, then the higher ratings of accuracy that our program outputs for unfamiliar teacher videos. So this indicates that our method of using feature angles as a medium for accuracy evaluation is in fact actually doing its job well, and it's standardizing the variances effectively, such as the different body measurements like mentioned before. And as expected, our model classifies 7 out of the 8 teacher videos from the testing data as needing no correction, and this is also a good sign because the teacher video. So this is as expected, basically, for teacher videos, right? And then for the 25 student videos in our testing data set, BalletNet Trainer outputs an overall rating of ranging from 0.58 to 0.78. So these are, as you can see, there's a trend of the student videos having a lower rating in general in comparison to the teacher test videos. And for dancers in training, this is as expected. And the overall outcome that the teacher videos received high scores, on the other hand, while the student videos did not. So this supports the hypothesis that the pirouette features extracted as the areas of study actually does effectively capture the aspects of the movement, such as alignment and etc., that actually makes the professional teacher videos correct and the student videos wrong in a sense. And next slide. So next is like an additional relationship or observation that we made, and it was so an additional thing that we to study is that if we use the information from neighboring frames, such as neighboring angles from the same joint, as opposed to just using the current or the single current frame, and if that actually optimizes the feedback efficacy, right? So as you can see here, we outputted the feedback of our program for when the data of the neighboring frames are used versus when they're not. So they're in the yellow and the orange. And we observed that the accuracy of the generated feedback actually increases by an average of 25.4% when neighboring data were used. And by accuracy, I mean how much did the feedback generated match the feedback given by the real life dance teachers. And so this is a huge deal, and that is a positive thing, meaning that it basically supports our hypothesis that using neighboring frame data does in fact help with the accuracy of the feedback given.
We had a couple limitations in our current program, one of which is the accuracy of the pose estimator that we use. So as technologies like the open pose innovate and become more accurate, the data that our application uses becomes more accurate as well. So over time, we will probably become more efficient and more accurate in the kind of feedback that we're able to give. And the second limitation that we had is the number of frames that we had available. So for a pirouette, that usually is around 30 to 35 frames. So with more frames, we would have more data and better feedback that we could generate because we could better understand the mistakes and the extent of the mistakes and use that more effectively. And future improvements that we can make to our program is that right now it's pretty specific to pirouettes. So this general pipeline, like Emily said at the beginning of our presentation, can be expanded to apply to other dance movements and other physical movements in general. So there's a lot of potential for growth that hasn't really been taken advantage of yet.
Right. Yep. Okay. And thank you guys for listening. Actually, we were about to summarize a few of our key contributions, but I'm not sure where this slide went. But yeah. Thank you guys. Is there any questions?
Yeah, I have one quick question. So you guys said that you guys got like 20 student videos from YouTube. How
Right.
long was each video in general?
Right. So good question. So to kind of standardize everything, we actually kept it really short. So it was about 2 rotations. So that would be around 1 point something seconds. And to transfer that into the amount of frames that we have, that would be around it would range from around 30 something frames to around 50. And using DTW, we can standardize them and match the frames.